The Zoom session is being brought to you by the Fractal Snow Ring, one of my favorites. Is that a cat out here? Excuse me. I have to throw them treats to make them leave the room. We proceed. Okay. Where are we at? Oh, yeah, we're talking. Okay. Today we go over matrix algebra, or really I should call it matrix arithmetic. We've seen matrices already. Augmented matrix, we put all the numbers in a linear system down in an array. So okay, that's called a matrix. A matrix is a block, an m by n array. It has m rows and n columns. The matrix A, then the entry in row I in column J is A sub ij. Two matrices are equal if they have all the same entries. A sub ij equals B sub ij for all I and j. They have an arithmetic. You can add matrices, subtract matrices, multiply and divide them. Subject to some conditions, the dimensions of the matrices have to match up properly. And we define these additions, subtractions, multiplications, and divisions in a way that helps us define linear systems. Okay, if we have two matrices that are both m by n, they can define their sum, their difference, and a real number times the matrix these ways. Oh, by the way, if a real number is also known as a scalar because it refers to the scale of a matrix. Later we'll see a row matrix, which is m by 1, or a column matrix, which is n by 1, or a row matrix, which is 1 by m. These are called vectors because they denote directions in space. We'll get to that later. Now, okay, the ijth entry of a sum is aij plus bij. You add entries. The ijth entry of a minus b is aij minus bij. You subtract entries. And the ijth entry of a real number times a is that real number times aij. You rescale entries. So for example, here we have the matrix 1, 2, 3, 4, and the matrix 10, 8, 9, 7. We'll define their sum, their difference, and twice a this way. A plus b, you add entries. 1 plus 10 makes 11. 2 plus 8 makes 10. 3 plus 9 in the lower left makes 12. And 4 plus 7 in the lower right makes 11. 11, 10, 12, 11. A minus b, you subtract entries. Upper left, 1 minus 10 is a negative 9. Upper right, 2 minus 8 is a negative 6. Lower left, 3 minus 9, the lower left entries, is a negative 6. And lower right is 4 minus 7, lower right entries, is negative 3. Twice matrix A, we double each of 1, 2, 3, 4. 2 times 1, 2 times 2, 2 times 3, and 2 times 4 makes 2, 4, 6, 8. So, okay, basically everything happens in parallel. So here's another example. 2, negative 5, 0, 7, 3, a half, 5, 1, negative 1, 3, and 2 minus 5, half, 0, 0, 2, negative 3 are matrices A, B, and C. So let's define 5A, C minus 5A, B plus C, and B minus C. 5A, you multiply each of these entries by 5. 2 times 5 is 10. 2 times negative 5 is negative 25. 2 times 0 is 5 times 0 is 0. My apologies. 7 times 5 is 35. So there we are. 10 negative 5 times 0, 35. C minus 5A. The problem is that we have to, if this is C and this is 5A, you really can't define their difference because the dimensions don't match up. This C is 2 by 3, 2 rows, 3 columns. And 5A is 2 by 2, 2 rows and only 2 columns. So you can't define the entry, 5 minus C minus 5A. So we don't define it. B plus C, you add entries. 3 plus 2 is 5. A half plus negative 5 halves is negative 2. 5 plus 0 is 5. 1 plus 0 is 1. Negative 1 plus 2 is 1. 3 plus negative 3 is 0. So this is B plus C. B minus C, we subtract entries. 3 minus 2 is 1. A half negative minus 5 halves is 3. 5 minus 0 is 5. 1 minus 0 is 1. -1 minus 2 is a -3, and 3 minus -3 is a 6. All right. Now we get to multiplying matrices. Here it gets a little complicated. We start with very specific matrices, a row vector, which is 1 by n, and a column vector, which is n by 1. You can multiply these two, provided these two n's are the same. This way, A times B is A1 B1 plus A2 B2 plus A3 B3 all the way down to n Bn. So we multiply corresponding entries and sum the total result, and that is called, well, it's a matrix product, but in the specific case, it's also called a dot product. All right, so 137 times 246, 1 times 2 plus 3 times 4 plus 7 times 6. After a bit of arithmetic, that's 56. Now, the way to multiply an n by m matrix by an m by p matrix, well, first of all, these m's have to be the same. The number of columns of A has to equal the number of rows of B for this to work. So you do this by multiplying the rows, A's rows by B's columns. So the ijth entry of A times B is the ith row of A times the jth column of B. A's row 1 is AI1, AI2, AI3, up to AIN. B's column J is AIJ by B2J all the way up to BNJ. And this product is what it is. AI1 times B1J plus AI2 times B2J, up to AIN times BNJ. So, for example, here we have a matrix A, 2, -5, 0, 7, 3, 1, 2, -1 is H. And AH, we divide A into rows and H into columns. 2, -5, 0, 7 are the rows of H. 3, 2, and 1, -1 are the columns of A. So upper left, we multiply the upper row, of A times the left column of H. 2 times 3 plus -5 times 2 here. Upper right entry, we multiply the upper row of A times the right column of H. 2 times 1 plus -5 times -1 here. Lower left, take the lower row of A times the left row of H. 0 times 3 plus 7 times 2 here. Lower right entry is lower row of A times the right column. Lower row of A times the right column of H. 0 times 1 plus 7 times -1 here. And after some arithmetic, it's -4, 7, 14, -7. Now, if we do HA, here's what we do. Here's H, 3, 1, 2, -1. Here's A, 2, -5, 0, 7. We divide H up into the rows 3, 1, 2, -1, and A into the columns 2, 0, -5, 7. And we do the same thing as before. Upper left entry of HA is upper row of H times left column of A. 3 times 2 plus 1 times 0 here. Upper right, upper row of H times right column of A. 3 times -5 plus 1 times 7 here. Lower left, lower row of H times left column of A. 2 times 2 plus -1 times 0 here. And lower left entry, lower row times right column, lower right times right column. 2 times -5 plus -1 times 7 here. And some arithmetic, you get 6, -8, 4, -17. You notice that these are not even close to each other. In fact, it doesn't have the same entries anywhere. So, okay, A times H is not equal to H times A. Matrix multiplication is not commutative. So it doesn't follow quite the same rules as numbers do. They're still useful. Here we have a 2 by 2 matrix A and a 2 by 3 matrix B. And we can still multiply them. So A times B, you divide A into rows and B into columns. Here's the way it works. This is 2 by 2 and this is 2 by 3. You skip out the middle 2's and get a 2 by 3 matrix. Upper left is upper times left 2 times 3 plus negative 5 times 7 here. Upper middle is upper times middle, 2 times 1 plus negative 5 times 2 here. Upper right is upper times right, 2 times 4 plus negative 5 times 1 here. And on the bottom, bottom left is bottom times left, 0 times 3 plus 7 times 7 as here. Bottom middle is bottom times middle, 0 times 1 plus 7 times 2 here. Bottom right is bottom times right, bottom row times right column, 0 times 4 plus 7 times 1 here. And here you go, negative 29, negative 8, 3, 49, 17, 14, 7. There it is. But if you try to multiply them the other way around, it doesn't work. B times A. B is 2 by 3, 2 rows, 3 columns. A is 2 by 2, but if you try and match these up, it doesn't work. This row has 3 entries, this column has only 2, so you can't match them up. This is 2 by 3, this matrix is 2 by 2. These two middle numbers, the number of rows of the first, columns of the first matrix must match the number of rows of the second matrix to be able to define the product at all. So in this case, it's not defined. Here we have a 3 times by 2 by a 3 by 2, and 2 and 3 don't match up, so this product is not defined. If, on the other hand, if you have this is 2 by 3, this is 3 by 2, these 3's match up, so you can define the matrix product. Here we go. Upper right is upper left is upper row 2, 1, 2 times left column 1, 3, 2, 2 times 1, 1 times 3, 2 times negative 2 here. Upper right is upper row times right column 2 times negative 2, 1 times 6, 2 times 0 here. Lower left is lower row times left column 6 times 1 plus 3 times 3 plus 4 times negative 2 goes here. And lower right, lower row times right column 6 times negative 2, 3 times plus 3 times 6 plus 4 times 0 here. And after some work, it's 1, 2, 4, 7, 6. Now, okay, I guess I could have multiplied these in the other direction and you'd have a 3 by 2 times a 2 by 3, and those two would match up, and so you could define the result. We'll get to that later. We have a 2 times 2 by a 2 times 3. Okay, these two match up, so you can multiply the product. I'll skip that over and get a result. But you couldn't swap them, because this 3 does not match this 2, so you can't define the product in the opposite direction. Now, there is a very special matrix which acts like the number 1. Here it's 2 by 2, 1, 0, 0, 1. Say 1's down the diagonal and 0's elsewhere. If you work out it times A, B, C, D, if you work it out, it turns out to be A, B, C, D, the same thing. And if you multiply them the other way around, 1, 0, 0, 1 times A, B, C, D, that too is A, B, C, D. So if we'll call this matrix I sub 2. It's a 2 by 2 matrix with 1's down the diagonal and 0's elsewhere. It's called a 2 by 2 identity matrix. Multiply 2 by 2 matrix times I2, you get back itself. It's like multiplying by 1. Here's I3, a 3 by 3 matrix with 1's down the diagonal and 0's elsewhere. Okay, it's a 3 by 3 identity matrix because if you multiply either on the left or the right by any other 3 by 3 matrix, you get that other matrix. AI3 times I3A is A. And in general, I sub n is an n by n matrix with 1's down the middle, down the diagonal, and 0's everywhere else. If A is n by n, then AI sub n equals IA sub n equals A. So this is an n by n version of the number 1. So, all right. So, okay, we can define identities. Later on, we'll soon define inverses, and that will enable us to solve linear systems. Here we can define powers of matrices. 5024 squared, well, it's it times itself. If you do a matrix multiplication, you get 25, 0, 18, 16. Simple enough. Third power of 5024 equals the second power times 5024. Well, this is this 25, 0, 18, 16 times 5024. And you go through the usual procedure and get 125, 0, and 122, 64. Fairly straightforward. Now, these matrices, they don't have all the same rules as numbers do, but they have many of the same ones. I mean, they don't have commutativity. A times H is not necessarily as H times A. But they do have a version of the identity operation. A times identity equals identity times A equals A. It also has a lot of the same rules for addition. A times B equals B, A plus B equals B plus A. It's commutative. It's associative. A plus B plus C is A plus B, that plus C. It's associative for scalar multiplication. C times dA equals CD times A. And it's distributive for scalar multiplication. C times A plus B is CA plus CB. For C and D being scalar, that is to say, real numbers. And it turns out that for matrices, distributivity also holds. So, and associativity. A times BC equals AB times C, if all the matrix products are defined. And A times B plus C is AB plus AC. B plus C times A is BC plus CA. So you have associativity for matrices, distributed left distributivity and right distributivity. But you don't have commutativity necessarily. AB does not always equal BA. All right, so those are some basics. Those are the basics of matrix arithmetic.